Hello again, and welcome to the next review video for Calculus 3208 to get you ready for your final exam, presented by CDLI. And we're still in the blanket topic of derivatives here, and this time we're actually going to speak specifically about comparing some graphs of derivatives, and we're going to throw a little bit of an extra topic in with that as well for time-wise. So we're going to compare the graphs of the original function f of x and the graph of its derivative, because that was, as we've seen already, the derivative can become a function unto itself. Alrighty, so we're going to talk the little extra topic we're throwing in along with this today. This business about higher order derivatives. So we'll talk about what that means. Then we're going to talk about how do we get a graph of a derivative function like f prime of x. So the graph of a slope function. And then we're going to compare some of the key features of the function f for its graph and the graph of its derivative f prime. Alrighty, let's get going. So the first thing we're going to talk about are those higher order derivatives, and it's really a simple idea to start with. Since y prime, or f prime of x, or dy over dx, or whatever the kids are calling it these days, is the derivative of the function f of x, and it, since we now know, can be a function unto itself, well, shouldn't it be able to have a derivative? So we can take the derivative of a derivative. So in other words, as long as this is a function, we can find its derivative as well. So then we get what we call that instead the first derivative, because if there's going to be more, like this one, we're going to have to give them all names. So, you know, better than Rudolph or something. So we'll call this one the second derivative. So that's, and the one thing we got to notice here is the notation that we use for that. So the second derivative we're going to call y double prime like that, or f double prime of x. And then we use this swanky notation over here if we want to be really particular. So we call it d squared y over dx squared, or sometimes d2y over dx2, but I like the squared one better. And we've also got a third derivative, so y triple prime, f triple prime, or d cubed y over dx cubed, like so. And after we get beyond the third derivative, we usually stop writing out these little tick marks like that, although some folks you'll see, and in some textbooks even, will use Roman numerals to pick up after that. So if we have the fourth derivative, sometimes you'll see it written that way, but you have to have those brackets or it's not quite correct. Same with f with this one or that one. But also for this, you may at some point see there's a different way to write that. So yeah, the different way to write that out is just to use Roman numerals instead of the numbers. So if you see this, that means the fourth derivative. But if you don't know your Roman numerals, I wouldn't sweat it. You're not going to see too much of it. And the nth derivative then would just be however many times you differentiate you get so far with it. Alrighty, let's move along. So what we're going to talk about is if derivatives can be functions unto themselves, which is how we're able to get those higher order things in the first place, what do the graphs look like? So what we did here is we've taken a graph of a cubic function, the one that's given on the left, and on that graph I plotted a whole bunch of tangent lines at different places. Because we know the derivative is really all about those tangent lines, isn't it? So the slopes of those tangent lines. And so what I've done is I've created a table of values down here. So there's 3 rows in this table. The first row is just a bunch of numbers for x, so going from 0 across the x-axis there. And then the f of x row is all of the y coordinates for those points. And then the f prime of x row is actually if you took each one of these tangents and you could measure its slope, which I did previously or before this, then I just wrote out what all those slopes would be. And so if I want to think about a derivative function, it's not a function that gives you the y values for the curve, it's the function that gives you the slopes for the curve. So then when I go to draw the graph of the derivative, its actual y values will be the slopes of the other graph. Interesting stuff. Okay. Okay, so if we want to draw a graph of the slope function, all we have to do is figure out the slopes of the graph over here and plot them at their corresponding values of x. So let's give that a whirl for this, and we'll see if we can get an idea of what this graph is going to look like. So when x equals 0, we're saying f prime of x is 1.9. So we'll put a dot right here because this line over here had a slope of about 1.9. And then when x equals 1, we've got a slope of 0. At 2, we're at negative 1.1, and so some of these we'll have to estimate a little bit, but we'll get a picture of it anyway. And when x equals 3, we're at minus 1.5, so minus 1.5 is in this neighborhood here. And when x equals 4, we've got negative 1.1, so back to that height again. when x equals 5, we have another 0. And when x equals 6, we're back up at 1.9. So you probably could have guessed it by now. If we're drawing the graph of a cubic, what we get is a quadratic. And this is review, so it's not like we're surprising you with any details here, except for the details of how poorly I'm able to draw graphs. Okay. If you've been following all of our videos through, however, that shouldn't be such a surprise either. Alrighty, so let's try that again. Make sure we get a little better curve here. So I'm going to try to draw the graph that starts out here and goes up this way. Try is the operative word in that sentence. So the parabola should look something like that. Alrighty, so we've got a graph of a parabola that we get as the derivative of that cubic that we started with. Let's jump ahead a bit now. So what I've done here is I've taken those two graphs, the one that was, and this time they're drawn by a computer, so you don't have to worry about my handwriting. That's the cubic that we had before. And here we have the graph of the parabola, that is the derivative function. And what I want to do is I want to look at some key points on both of those graphs in terms of where the x values are. So the ones I want to look specifically at are at x equals 1 and at x equals 5. Okay? And then I want to look at the intervals in between those places. So what I'm going to do here is I'm going to draw a line on this graph at x equals 1, and then I'm going to draw a line at x equals 5, vertical lines that is, so that we can get a pretty good idea of what's happening. So at x equals 1, I want you to see how everything lines up here for the x coordinates. And then at x equals 5, I'm going to try to do something similar over here and draw another vertical line, just so we can see how that lines up. Those lines are not part of the graphs of either function, so don't let that mix you up. They're just, sorry, just on there as an aid for now. And I want you to notice the relationship between the graph of f, which is this one up here, and f prime, which is this guy down here. And what I want you to see is that up here, this is a vertex or a local maximum point on f, and notice that f prime is actually equal to 0. And notice over here that when we have this vertex, which is a local minimum, f prime is also equal to 0. And those correspondences shouldn't be surprising if you're familiar with the idea of horizontal tangents. So if I were to draw a tangent line on here, on the top curve, and then another one down here, we can see that at those points, the tangent lines turn out to be horizontal lines, which is why the derivative has a value of 0 and therefore an x-intercept. So what I've done is I've created a little number line over here on the right, and that little number line that's over here on the right is for me to do an analysis of this. So I'm going to circle the coordinates for x at 1 and at 5. And then I'm going to make a note that my derivative is actually equal to 0 at both 1 and 5, which means that my function f has a local min or a local max. And what I want you to look at now is the graph of the derivative, and I want you to notice that out on this side, so everywhere to the left of that positive 1, our graph is up above the x-axis, meaning that our slopes are all positive on the original function. And notice that the original function is actually increasing out there. So the way I like to draw that on this diagram, so I like to say f prime is positive, which means that f is on the way up. In between these 2 points that we talked about, notice that our derivative is below the x-axis down here. And since our derivative is below the x-axis, our original function is decreasing because it has negative slopes. So out here, we've got a negative value for the derivative, and the original function is on its way down. Then, to the right of the 5, we've got the same kind of behavior we had in our first interval. The derivative is positive, so the original function is increasing. Alrighty, excuse me. So once we get all that put together, here's what we notice about the relationships here. We can see that since f is increasing and then decreasing and had a horizontal tangent right here, then this is going to make it a local max, which is exactly what we see on the graph. And at 5, we're going to have a local min. So we can see those things happening. So if I wanted to write all that in tabular format, which is the way some folks prefer to do it, as opposed to on a number line like up here, then I would say that f prime is positive 0, it's negative in between, it's 0 at 5, and then it's positive again. And that tells me that my original function is going to be increasing to a max value, and then it's decreasing to a min value before it finally increases again forever as far as we can tell. Okay, so there's a bit of an analysis to show you the associations between what the graph of f and f prime do at similar values of x. So let's, using that information, see if we can match the graph of each of the functions that are given here on the left with the graph of the appropriate derivative that's given here on the right. Okay, so for the first one, let's look at this graph. We've got to have a function that's decreasing, and then it's going to have a horizontal tangent there, and then it increases to have another horizontal tangent, and then it decreases. So its derivative should be negative, and then 0 right around there, and then positive, and then 0 right around there, and then negative again for its derivative. Okay, so let's see. Which one of these goes negative, and then positive, and then negative? I think it's this one right here. So if we look at that graph, excuse me, if we look at the graph for the second one here, number 2, we can see that we had a negative out in this area, and then we had a 0, and then we had a positive up in here, and then it was 0 again. And notice that the coordinates, or roughly the x coordinates for these vertices, line up with the zeros on the derivative. Okay, so the next one we're going to look at is this graph B right here, and see if we can find its derivative. Now notice that this guy is really jagged, and it's like got these sharp corners going on up there. So for that one, what we're going to have to do is we're going to have to be careful about how we would think its derivative would look. So the derivative is going to be positive here because it's increasing, but it's constant. And if something is constant and not changing, it should be a horizontal line. Then in here it's got to be negative and constant, and out here it's going to be positive and constant. And at both of these points, if you remember from our differentiability talks that we've had, then we're not going to be able to find the value of the derivative at all. So it should be discontinuous for a derivative, and that obviously is going to line up with this one, graph number 4. Okay, so then for part C here, we're going to look for a graph that, for the graph of the derivative, that shows us that our original function is decreasing and then it's increasing, which means our derivative has to be negative and then positive. And of the two options we have left, the only one that can make that work is number 1. And so obviously part D has to be number 3 here. Let's see, increase, then decrease, then increase, then decrease. So let's see what that means down here. It's positive, negative, positive, negative. Exactly. Okay, so that's how we match those up. So hopefully that wasn't too confusing for you. So in this case, what we actually have to do is we have to sketch the graph of the derivative of the set of axes that's given below each particular graph. So for this first one, we start off with negative and constant until we get up to that first corner point there. And then we're positive and constant until we get up to 0. And then we're negative and constant until we get up to our next corner point. And then we're positive and constant again from there on to infinity. So I missed a little bit with this one. I'm going to move it just a little bit that way so it doesn't look like it's too close to the y-axis on us. So the idea here is that we've got the graph of the derivative that's discontinuous. And notice at these points I'd have to put open circles on my graph here because our actual original function is not differentiable, so there are no values of the derivative there. So that's roughly what that one would look like. Now we'll try the next one. And for the next one, well, we can see that we're going to have a horizontal tangent line here, and we're going to have a horizontal tangent line there. So those should be the zeros on the graph of my derivative. So I'm trying to line those up the best as I can directly below that. So those will be my zeros, but they don't necessarily correspond to vertices or max-min values. This point right here, we're going to be decreasing before and decreasing after, which means my derivative has to be negative until I get there, and it has to be negative again after that point. So I should try to draw that as a smoother curve, I suppose. So let's make a nice smooth curve that goes up and touches there. So it should look something like that. Let's clean that up a bit. Sorry about that. So we'll get all that stuff out of there, and we'll draw a nice smooth curve. All right. So we're going to have this point right here being okay, and then a nice smooth curve that comes up to it and then bounces off. And then our derivative should have to be negative because this curve decreases all the way down to there. So we've got to stay negative until we get to that point, so we're below the x-axis, after which the original function is increasing, so we're allowed to be positive again. So our derivative would look roughly like that. And for this next one, we'll first identify this point right here, vertical tangent line. So no value for the derivative there, but we can see that our derivative should be positive because we increase up to that point, and it should continue to be positive after that point. So it starts off fairly small, and then it gets really, really, really huge. The derivative, we're approaching vertical tangent line, which means that our derivative is going to be asymptotic this way. It's going to get super huge. And then as we come from the other side, we're going to do exactly the opposite behavior and level out. But the derivative is always positive because these slopes up here will always be positive because this function is always increasing. Okay? So that's a rough idea of what those graphs are going to look like. So here's another question. It says, which of the following is ordered correctly based on the graph of f of x shown? So this is f here, not f prime. So we're looking at a graph of f of x. And the first one, and actually all of them, we're looking at when x is 4, 0, and 1, and they're looking at values of first and second derivatives here. So we get lots of things to compare. So let's look at values at 0, 1, and 4. So let's at 0, right here, what we have is a negative slope. So we know that f prime of 4 should be a negative number. And, oh sorry, f prime of 0, excuse me, should be a negative number. And at 4, we've got a negative slope again that looks even steeper than the last one. So I'm going to say that this one is also negative at 4. So f prime at 4 is also negative, but if it's steeper, it's got to be a bigger negative number, so it's actually less than that one. And then we want to look at 1. So at 1, we've got this horizontal tangent going on here. And that means my derivative is actually equal to 0. So right here, f prime of 1 is actually equal to 0. So we've got to at least have those three things, if they all come together in one of these, in that order. So I see that happening here, and I see it happening up here. The rest of these don't have those three things in the correct order. So which one of those is going to be correct? Well, it's this business with the second derivative that's going on here. And the second derivative, if you remember, is the derivative of the derivative. So if your slopes are in the process of getting steeper, then their rate of change for your derivative will be positive. And if your slopes are in the process of getting more negative or getting less steep, your second derivative is going to be a negative number. So let's look at let's see what's going on. We can see that the slopes are getting less negative and then more positive here. So the slopes are increasing, which tells me that f double prime at 1 has to be a positive number. So the only one that's going to make all of that work is going to be part A. So there's our option there. Alrighty, let's roll along. Here's the your-turn question. All you have to do here is sketch the graph of f prime of x directly on the same set of axes. And there's the solution that's given for you, and I actually included with the solution a number line down here, which will help you out a little bit if you want to remember how we compare f prime and f as such. And then we'll highlight some of the key features of things that we saw here today. So we're going to talk about the second derivative of a function as being the derivative of the derivative, and similarly we get third, fourth, etc. The graph of the derivative function is found by plotting the numerical values of the slopes of the original function against the same values of x. And when sketching the function, we should look for some key features. So horizontal tangents on the original will produce zeros for the derivative. Points where we're not differentiable on the original will give us either a discontinuity or a vertical tangent or a corner or some of those examples like we saw here. And moving left to right on the graph, if f of x increases, then f prime is positive, and if f of x decreases, f prime is negative. And that should be all the fun stuff that we need to do those things. All right, hope that was helpful.